This is section 3.2. 3.2 is about algebraic vectors. We saw in section 3.1 what an algebraic vector looked like. In 3.2 we do a little bit more with them and find out what they're good for, which is calculations. So this is why we have algebraic vectors to start with. So let's take a look at section 3.2, algebraic vectors. All right, first of all, we have added vectors before. To add vectors, add corresponding components. We've added vectors because we've added matrices. And when we added matrices, we added corresponding components. For example, if you had the vector 1, 2 plus the vector negative 2, 4, we get the vector negative 1, 6. You just add straight across. So 1 plus negative 2, negative 1, and then 2 plus 4 is 6. When we add two vectors, in real life, we're finding the resultant force. Now, by resultant force, you can think of that as meaning like sum force. A classic example is if we have a pin, look at my little yellow pin there, being pulled in two directions. So this pin is like stuck into a piece of paper or stuck into a board or something, and it's being pulled in this direction by vector v. Then it's being pulled in that direction by vector u. I want to know what that pin really feels. In other words, if it flies out of the board or it flies out of the paper, where's it going to go? Okay, well, the place it's going to go is the resultant, which is you'd pick up the u, basically, put it at the end of v, pick up the v, put it at the end of u, and you form yourself a parallelogram. The diagonal of that parallelogram, the orange line there, is u plus v. Okay, so that is going to be what the pin actually feels. That's the resultant force, is the diagonal of the parallelogram you form. Okay, let's look at our previous example. We had 1, 2 plus negative 2, 4. We said that was equal to negative 1, 6. What I want to be able to do now is graph that. I want to draw geometric vectors representing these, representing this sum. So I want to be able to draw something for the vector 1, 2. So I want to call that u. And then v, I'm going to let that be negative 2, 4. So I have the vector 1, 2 and the vector negative 2, 4. Okay, for the vector 1, 2, if you remember what I do with the position vector, it goes from 0, 0 to b1 minus a1, b2 minus a2. We'll already have that figured out. So that's going to be 1, 2. So there's the vector u. The vector v went from 0, 0 to negative 2, 4. So there's the vector v. And what I want to be able to see is if I add those two together using, good old algebra, matrix algebra like we did before, do I get the same picture as if I pick up v, put it at the end of u, pick up u, put it at the end of v, form a parallelogram, etc. Okay, well again, if you look at the diagonal of that parallelogram, the diagonal of that parallelogram is pointing at the point negative 1, 6. And that's exactly what I got when I added the two vectors together. I got negative 1, 6 for the result. Okay, so hey, it worked. That's pretty good news, right? 1, 2 plus negative 2, 4 was equal to negative 1, 6, the vector. And again, the position vector for that would be pointing at negative 1, 6, and it sure does. Okay, another example. This time, let's let A be 3, negative 1, B is 6, 4, C is 3, 2, and D is 7, 2. If U is AB, so U goes from the point A to the point B, and V goes from the point C to the point D, first of all, I want to find U plus V, and then I want to find a K such that U plus V is equal to AK. All right, so I ought to probably find u and v, first of all. Find the algebraic vectors for each of those. Okay, so for u, I want to do 6 minus 3 and then 4 minus negative 1, so I get 3, 5 for u. Then for v, since that's CD, I want to do 7 minus 3 and 2 minus 2, and I get 4, 0. Okay, so now I have u and v. It's pretty quick to find u plus v now. U plus v is just going to be 3, 5 plus 4, 0. Add your corresponding entries and you get 7, 5. Now, this business of finding a point k. What I'm going to have to do now is set up k to be k1, k2. And I want it to go from a to k. So I take the values of a and I subtract them from the values of k. So I do k1 minus 3, then k2 plus 1. And I set that equal to 7, 5. Okay, a little bit of algebra. K1 minus 3 is 7, so K1's got to be a 10. K2 plus 1 is 5, so K2's got to be a 4. K turns out to be the point 10, 4. Okay, a little bit more. If we now were to go and graph AB, that vector, and the CD vector, which as you see is just a little horizontal segment there, and I want to find the picture that represents the resultant. So I want to be able to add those two vectors together. Now what we said is we can pick up one and put it at the end of the other. Now the thing is they don't have the same starting point this time. Turns out it doesn't actually matter which one you pick up and move. Okay, but you want to translate one of them so that it has the same starting point as the other. Now I'm going to choose based on the fact that I wanted my sum to start at A. So in order to draw that picture, I'm going to go ahead and move CD down to AB. So I'm going to leave AB where it is, in other words. And as you see, I moved the CD up and then down, forming my parallelogram, so that this way I can start at A and end up at K. Okay, it is expressly because it said I want to go from A to K. All right, so as you saw, I got the K value there of 10, 4. Okay, so that was section 3.2. We did a little bit of work with algebraic vectors. As you saw, you already knew how to do a lot of it already, but we drew some pictures. Specifically, we drew the sum of two vectors, which turned out to be the diagonal of the parallelogram that they form. So you'll just need to pick one of them up, slide it over, keep working with that, picking them up, sliding them around until you get a parallelogram, draw the diagonal, and that's the sum.